Yes, good morning everyone. The very most important theorem is now we are going to start. In Rk, every Cauchy sequence converges. This we need to prove. And one more small concept of complete metric spaces, right? So let's start. So this is a very important theorem. In Rk, every Cauchy sequence converges. Before this theorem we have done that Cauchy sequence converges in a compact metric spaces, right? Here it is now we have to prove that the Cauchy sequence converges in Rk. Rk is your Euclidean space, right? So let's start with the proof. So let's suppose we have given a Cauchy sequence. So let's suppose that let Pn be a Cauchy sequence in Rk. We need to prove that this sequence is converging in this Rk. So the steps are very similar to the theorem we have done earlier. Again, we have to define our En. So I just read out the proof. For n equal to 1, 2, 3, let En is equal to Pn, where n is greater than equal to capital N, which is equal to Pn, Pn plus 1, so on. Then limit n tends to infinity, diameter for this En is equal to 0, which implies limit n tends to infinity, diameter for En bar is also equal to 0, where En bar is the closure of En. And why this has happened? Because we have already proved that diameter for En is equal to diameter for En bar, right? Now we have to choose a epsilon. We have to use the definition for the convergence on this diameter for this En equal to 0 when limit n tends to infinity. We have to use the definition for the convergence here, taking our epsilon to be equal to 1. So we have to choose our epsilon here. So since limit n to infinity, diameter for En is equal to 0. So therefore we are choosing our epsilon to be equal to 1. Then there exists a positive integer m such that diameter of En will be strictly less than epsilon. So instead of epsilon, I'm writing that diameter for En is strictly less than 1 because I have choose this epsilon to be equal to 1 for n greater than equal to m. So can I write in particular diameter for, instead of En, can I write Em? Why? Because this diameter for En strictly less than 1 is for n greater than equal to m. So n is starting from either m or greater than m. So this thing is true for n equal to m also. So can I write instead of En, Em strictly less than 1. This is just in particular I have written, right? Now because this diameter for Em less than 1 means the distance between the points for Em is the supremum distance is strictly less than 1 means it is bounded, right? So if the diameter for Em is strictly less than 1, that means this Em is bounded. So thus Em is bounded because it has its bounds, right? Now what is actually Em is? From where this Em start? See, Em starts from, because En will start from Pn plus 1, Pn plus 2. So Em will be starting from Pm plus 1, Pm plus 2, up to so on, right? And this Em will be equal to this plus the union. The remaining points will be P1, P2 up to, because this is from Pm, so the remaining points will be up to Pm minus 1. Clear? Now, this is your, this Em is bounded. That means all these points which are defined here, these are also a bounded one, and this is your finite set. Right? So, if Em is bounded, that means the range for Pn is the union of this Em and finite set. This is your Em. So this is the range of Pm, sorry. This is your Em. This is just your range of Pn. This Em is bounded, we have written here, and these are the remaining finite set. So a finite set is also bounded. So the range of Pn will be the union of these two sets, and the finite union of sets is a finite set. This is bounded, this is bounded. That means union of bounded set is also bounded set. So the range of Pn is also a bounded set. So can I write, therefore, the range of Pn is bounded, as Pn is also your Cauchy sequence. Thus, whenever the range is bounded means that sequence is bounded. You know, if your sequence is like -1, 1, -1, 1, suppose the sequence will be as this. Suppose this will be your sequence, so on. What is the range for this sequence? The range is -1 and 1. What is the meaning of the range? The distinct points of the sequence. So this is a distinct points of the sequence, right? And it is a finite set, it is a bounded set. Hence, this sequence is also bounded because this range is bounded. Similarly, if the range of Pn is, this is the range of Pn, the Em set union the remaining points. So if the range of Pn, that means if the range is bounded, as Em is also bounded, finite set is also a bounded set. So if the range of Pn is bounded, that means this Pn is also a bounded sequence. So thus the sequence Pn is bounded. Clear? Now, if the sequence is bounded, that means this sequence is contained in a closed and bounded subset of the metric space which we have given, that is Rk. So let's say that closed and bounded subset be X, where this sequence is bounded. So since Pn is a bounded sequence, so it must contained in a closed and bounded subset of Rk. So hence, as the sequence is bounded, the sequence Pn is contained in a closed and bounded subset X of Rk, right? So we have defined that subset to be X. So now X will be your closed and bounded in Rk. If X is closed and bounded in Rk, that means every closed and bounded subset of Rk is compact. This is a result. So since X is closed and bounded, subset of Rk, therefore X is compact in Rk. Now we have found a compact set in Rk and our sequence is in the compact set. And then again we have to just revise, we have to just write the similar proof which we have done in the theorem before this theorem, in the last video. The proof is same because we have found a compact space, and the last theorem is what? That if Pn is a Cauchy sequence in a compact metric space, then it is converging in X. We have to just revise that proof. So we have found a compact space X, and we are also having a sequence, Cauchy sequence in this X, right? So just repeat the proof. Since En bar is a closed subset of a compact set X, En bar is a closed subset of this compact set X. That means, and every closed subset of a compact set is compact. This is also a result. So En bar is compact as it is a closed subset of a compact set. Now since En contains En plus 1 for all n belonging to n, and En bar, that means if En is containing En plus 1, its closure is also containing closure of En plus 1. Now since En bar is what? It is just a sequence of compact sets. Because En bar is compact, so En bar sequence, this is a sequence of compact sets, such that En bar contains En plus 1 bar for all n belonging to n, and also the diameter for En bar is 0 when limit n tends to infinity. So therefore, all the intersections of En bar consist of exactly one point. And we say that point to be as small p, which is belonging to X, right? See, our sequence is in X. And X is further is in Rk. Thus, there is precisely one point P belonging to X which belongs to each En bar, right? Because En bar is containing En plus 1 bar. You remember? If this is E1 bar, this is E2 bar, so on. So the point, this P will be, because intersections of all these Ens is what? This set. That means this point P is containing in all these, each of these En bars, right? So now we again let epsilon positive be given, and since limit n tends to infinity, diameter for En bar is equal to 0. Now again I am writing the definition for convergence. See, whenever limit is equal to some, if it is 0, then that means if you take this 0 on the other side, the mod for diameter En bar minus 0 mod, that is less than epsilon for n greater than equal to m. This is the definition for convergence, right? So here the limit is 0. That means there exists a positive integer m such that this diameter for En bar is strictly less than epsilon for n greater than equal to m. Now since P is belonging to En bar, right, and our sequence En bar is containing also the sequence Pn. So therefore the distance between the 2 points of En bar, that means P and Pn, P is also containing in En bar, Pn is also containing in En bar. So both their distances is strictly less than epsilon for n greater than equal to m. Because if what is the diameter for En bar? That is the supremum distance between the points of En bar is strictly less than epsilon. If the supremum distance is less than epsilon, that means any distance you take with the point P is strictly less than epsilon, right? And our epsilon was arbitrary, therefore Pn is converging to P. And since P is in X and X is further is a subset of Rk, that means this P will now belonging to this Rk. That means our Cauchy sequence, which is converging to this P, is converging in Rk. Proof is done, right? So now the concept for the complete metric spaces. What are complete metric spaces? Actually, the metric space in which every Cauchy sequence converges is said to be a complete metric space. So right now we have done this theorem, that is our Cauchy sequence is converging in Rk. That means Rk is complete. So a space in which, a metric space in which every Cauchy sequence converges is complete metric space. So Rk is complete, and compact metric spaces is also complete, because we have done the result that Cauchy sequence in compact metric spaces converges, right? So these two theorems which we have done today and a theorem in the last video, these two theorems, guys, are very, very important one, and also explaining the definition for the complete metric space. So we have two spaces, compact metric spaces and Euclidean spaces Rk. Is Q, that is rational, Q is set of rational numbers. Is the Cauchy sequence converging in Q? We have done this example earlier. Is Q is a complete metric space? No, 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 no. Because if you consider a Cauchy sequence as 1, 1.4, 1.41, 1.414, so on. It is a Cauchy sequence in a metric space Q, right? Here the metric space is Q. It is a Cauchy sequence. Now where this sequence converges? This sequence is converging to root 2, and root 2 does not belonging to this Q. If the point, this is your point P. If this point P does not belonging to the space where we are having a Cauchy sequence, that means this Q cannot be complete metric space, right? So Cauchy sequence does not converge in this Q, right? So Q is not a complete metric space. So where the Cauchy sequence converges? In compact metric spaces and Euclidean spaces. Now above theorems can also be asked, like prove that every compact metric space is complete. So you just have to prove this theorem. If X is a compact metric space and if Pn is a Cauchy sequence in X, then Pn converges to a point of X. We have done this theorem in the last video. And today's theorem can also be asked, like prove that Rk is complete. So instead of, now the today's theorem is in Rk every Cauchy sequence converges. So this theorem can be asked as prove that Rk is complete. Both these results are one of the same thing, right? Okay guys, today's video is over. Next time we will be doing some more examples and concept for we have to do some more examples on this, and then the upper lower limits of sequence of real numbers. So have a good and lovely day. God bless you all.